Okay. Everyone, if you have a question about anything, you can ask now. Any administrative things? Any questions? You can use mic or chat. All right. I will try to go slow. Convex supposed to be for the next week as well, so I'll try to stretch. This is a bird course. So, okay, let's start. We want to minimize this function. So, can someone tell me what is the gradient of f equal to? Huh? Gradient of f? Didn't we do it last time? So that looks terrible. Yeah, so it's ax plus q, and just so that you know how to do this, always write it in coordinates so that you don't get lost in the notations. And then gradient is take partial in k. So the only guy that survives is what? Yeah, so you take it once, and this would be a transpose there, right? Okay, let's do it. So you do it once, you have xk summation in I, all right? ij with xi over here, and same thing, right? So you do product rule, and you're left with a summation of aij xi, and then yeah, so then you have this guy because you took its derivative, but then it came back inside. So you can write it like this: xk I not k, like this. Is that okay? Huh? What? Yeah, is that okay? It's disgusting. I don't know why I wrote it like. Is there a better way to write this? Oh, no. You guys should correct me. I'm going too fast. All right, there's nothing left. There's only one guy, AIK. A, and then this is K. All right. And then this is KK. Okay. Are you with me? Maybe I should go. So the question is find the gradient of the XAX. And unfortunately, xk shows up in both sums. So then I clean it up a bit by keeping one dxk, right? And so then, yeah, you have to do product rule. First one, xk is 1, and then the second one, you slide with the kk. Okay, so then, yeah, you have to do product rule. First one, xk is 1, and then the second one, you slide with the kk. Okay, so then, yeah, you have to do product rule. First one, xk is 1, and then the second one, you slide with the kk. Okay, so then, yeah, you have to do product rule. First one, xk is 1, and then the second one, you slide with the kk. Good for you. Now what? So we have to be more precise. It's AX, and then you have to multiply the diagonal of A. So take diagonal of A and multiply it by X. And then you add Q as well. Okay? Is that okay? Any comments? No, this is the gradient, not nabla. But yeah. Oh, that's right. That's right. Yes, there's another AKK. Yes. So this guy is squared. What? Wait, there is no. What are you talking about? Okay, you know what? Slow down. What are you talking about? The first one? Yeah, here I have another sum, but only the xk survives. Yeah, so you have to do product because there's two instances of xk. So, okay, I knew this is gonna be a mess. Let me do it slowly, okay? F of x is equal to what? Xk times the sum from I1 to n, including k, of I, k, xi, and then you have the other terms. So j not k, n, and then x, and then summation of I1 to n, x j, aij, xj, okay? And then, now on top, you have to do product rule. So when I take partial in xk, here you have to do product rule. So you get the summation, right? Then you get xk stays here, but then you take derivative of this sum, and you only survive the kk guy. Okay, and then the problem, yeah, so we have to be very careful with the other one. So this guy, you're supposed to write it again as xk summation j not k to n a k j xj plus other non-k terms. So I not k, j not k. Does that make sense? The guys that don't have any xk term die out. These guys are all dead. And this guy here survives. So you have one more term. So over here, you take derivative of this, so you have summation j not k of n akj xj. So then you add them up and you get 2 times summation of I. Oh, is that what you meant? Huh? So I need, okay, I'm assuming asymmetric. All this time I've been doing stuff for asymmetric. That's why I'm, so of course, you can, is that what you meant, that you're gonna get a transpose? Okay, let me finish it here, because, so, um, so where am I? Okay, so then, you get summation of I, AIKXI, plus summation of J1 to N of AKJXJ. Okay, so in other words, this is the following guy. So gradient of F, when F is just A X transpose X, it will be AX plus A transpose X. Is that okay? Yeah. Good. Yeah, what the hell am I writing here? So this is AX plus A transpose X plus Q. And then if you take gradient again, you get A plus A transpose. Yeah. Right, but we want to minimize this. So let me do it. Let me create some space and minimize it. Okay. So what's the minimizer when I know gradient of F is this? How do I find minimizer? Huh? I don't think it has a nice solution. So but yeah, you will need to invert this. So suppose A transpose is invertible. So then the minimizer is that. And how about knowing that this guy is a local min? What do I need? Given that the Hessian is A plus A transpose, what do I need my matrix to satisfy? Which is what? Can you give me one of the definitions? Because you will need to know it today, so that's why I'm asking. How do you check a matrix is positive definite? Sorry, what? Yeah, but like actually, I want to give you a quick way to do it. But yeah, for the definition is that V transpose A transpose is strictly positive for all V in Rn. That gives you a local minimum. So this X star is a local minimum. Okay. If your matrix is 2 by 2, here's another way. You just, yeah, you compute. So if 2 by 2, A, B, C, D, you just have to check that A is positive and the determinant is positive. So A D minus CB is positive. Okay. In other words, people also say the trace of A is positive. Because if you put these two together, you get that lambda 1, lambda 2 are the eigenvalues. Because it's not obvious, right? Like you guys use reversing criterion, but the proof goes through eigenvalues, right? And then you compute the eigenvector. You get like lambda 1. Okay, I'm not gonna go too into it, but you can have like lambda 1 b squared, and this is like oh. Let's do a more disgusting example. It's gonna be fun. All right. Can one of you tell me what's the Hessian of this function? What's the first component? Yep. What's the 1 over y derivative? Huh? First thing. Yeah. With a minus. Is that what you said? Okay, so what did you say? I mean, anyway, this is the answer, like partial y. Oh yeah, where is the 2x? Yeah. Right? Yeah. Okay, so where is the minimizer? Yeah, anyways. Yeah. Okay, so now let's compute the Hessian. So
I have a question. Where do you
yes,
get,
question.
where do you get the -2 for the y component when you find the partial derivative for y?
There is no -2.
Okay.
Yes, it's just the minus. I will come back to reality. I'm still doing my research. I'll be here. Yes, what's the Hessian on top? First component. Second. Two x over what? By the way, this is y squared. Yeah. 2x over what? Huh? Same thing, right? Y squared with a minus, right? Just to remind you, this is partial x, partial y, first component, and the second row is the second component. Yeah? Okay, what's the third entry? What is it? So what should I put? Oh, it's the same, yeah, it's symmetric. Yes, okay. What about the final one? This is hard. Oh no, it's one more, yeah. So what is it? It's good practice for the real thing. What's really
2x squared over y cubed.
Yeah. This looks terrible, but who cares? What happens at the minimizer? What's the Hessian? Huh? What? 2 over y, 0, 0, 0. So it's no negative definite. So what did I want to say? Okay, anyway, so with our results, you can only get like a local min. Yeah, you still get a local minimum, right? Is well, okay. We need it strict. What was my question? Let's see. Yeah, so right. So this is the minimizer, but it's not a global min. So that's why we get this flatness. It has like that's why we get the hasting to be zero, because there is a direction where you're like constant. You're not decreasing. Okay. So this is called a saddle, right? Because there are directions where you go up, but along the x equals 0 axis, you're constant, equal to 0. Do you understand? So this is all of them are minimizers, but they're not local min, because in the neighborhood of it, you're constant. You're not strict local min. You are a local minimum, but not a strict one. Do you understand? Is that okay? All right. So that's what happens when the Hessian is 0. So when you have, so we will come back to this, but I just want to make a point that it's not positive definite, so you lost strict local min, but you still have local min. Okay? Can I go? Yeah. So yeah. So yes, x equals 0 are the minimizers. Minimizers, but no global mean exists. Okay, and no strict local mean exists either. Okay, so the minimizer is at 0 and it's always 0. This is a very beautiful function. If you go into statistics, you will see it, or neural nets, whatever they call it now. Data, big data. So this log summation of e to the xi is very interesting. And it has the following properties. It's close to the maximum up to the dimension. Okay. And also it approximates it. So I'll leave that to you. It's a nice exercise and walk down. As you take epsilon to 0, this function called LSC in there goes to the maximum. Now, why do you want to do this? Maximum is not differentiable. Here's a picture. You see this cusp. Remember from 1 to 7, the absolute value is not differentiable. This guy is, and it's almost like the maximum. And in applications, you want to do numerics, so you want to take derivatives, like Euler method. So you go to this guy instead of computing the max. So I'm going to do minimization for it, so you have an idea of its properties and why people care about it. All right. So yeah, we have to do minimization. So we will compute the gradient and Hessian. So I take partial derivatives. One trick you might see later is change variables. How many you said? So I do the change variables zj, dxj, and I rewrite this guy as log of 1 dotted with z, right? Because 1 dotted z would just be 1 times exi y1 to n, okay? Just to keep everything compact, because the notation will get out of hand when you do testing. All right, so this is the formula for chain rule. If you want to take a different derivative, you have to multiply by its own xi derivative. Good. So if you do that, this is a 1D question. You just get 1 over the dot product. Okay, so nothing fancy here. All right. Good. And next, we compute the Hessian. So we take a different zi derivative. Again, you have to do chain rule. So let me explain what happened here. So dzi dxi is just partial exi dxi, so you get exi again. Here you do what is called quotient rule. Yeah, good memories. So you have 1 dotted z squared, and yeah, so I take derivative of zj, and this only exists when they're equal. So that's why we put delta ij, which is just meaning 1 when I is j, 0 when I is not j, right? Because, which is this partial zi zj. Is that okay? Huh? Does that make sense? Okay. So I do this, and then I multiply by the guy underneath, 1 tz, and yeah, we just have zj. And the derivative of the dot product is just once. So you just get a 1 here. I'm just filling in the steps. So that's that. And then we clean it up a bit. We bring in the zj. So this guy is a zi. And there's a very beautiful formula. Not yet. This is disgusting. No, it's there on the slide. Let me write the formula. So the formula is diagonal of z over 1t dotted z minus, we didn't miss much, z dotted z 1 dotted z squared. Okay. Can you imagine if I had ex there? It would be a nightmare. So again, z is the vector of ex1, exn. All right, so that's the Hessian. And I think at the next step, I show you that it's positive. Yeah. So we can show that it's positive, I mean, semi-definite. Okay, I jumped too much. So let me explain how you do this. I will do it on the side. So you have V, let me do this one first. So it was diagonal of Z. Diagonal of Z dotted with V, and then V transpose. So I'll do this one first. Do you know what diagonal of Z means? It's the identity matrix. Z1, Zn, 0, 0, V1 to Vn, and V1 to Vn. Okay? Is that okay? All right. If you multiply them out, you get first Z1, V1, Zn, Vn, and you do it again, and you get summation of Vi squared Zn. This is this guy. All right. Now I'll do the next term. Z dot T. You might see this, so I'll do it slow. So here I'm gonna compute for you Z transpose V. So note a common mistake. V transpose V transpose is a number. Okay. V1 Vn. Is that how do people write transpose? How do people write that? That doesn't matter. I have to be consistent. Let me do it this way. So you multiply and you get dot product. If you flip it, you get a matrix. Do you remember that? So here you do V1, Vn, Vn, and you get a matrix. So let me write the matrix. So you take the first entry and you multiply the vector. So we have V1 squared, V1, V2, V1, Vn. You take the second entry, V2, V1, V2 squared, V2, Vn. So 1 down to Vn squared and V1, Vn. Okay? There must be a closed form to write this, no? This is the closed form. Listen, you might see this, so I wanted you to see this because we're going to use it right now. So I have to multiply this. So we have the V's, and we have this massive, disgusting matrix. Right? Oh, and it's symmetric, which is pretty nice. Okay, and let me make sure. So we have to get squared. All right, let's do this. So we have to get a vector from here. So we have, I have to write it in closed form because this is terrible. It will be Z1 V1. So it will be Z1 times summation of Zi Vi, Z2 summation of same thing, Zi Vi, and down to Zn summation of Zi Vi. Okay, and then you put them again together and you will get this. Now let me show you the faster way. If you remember 244. This, so do not do what I just did. It was just to show you the power of linear algebra. So here's the power of linear algebra. This guy is equal to the following thing. V transpose Z dotted with VZ transpose. with a transport rate. Yeah, do you remember that? But they both equal to summation of VI ZI, VI ZI. So you get this guy squared. Is that cool? That's why you come to university, for this stupid tricks. That's, that's the only reason. Your CS friend would be like numerics, MATLAB. Like, yeah, here's how you do it. All right, so this is the squared. And then, have you seen crosses work? In which course? Huh? Like, did you, oh no, 244. Actually, you didn't see it in 240. Oh, actually, you did see it, but for a few seconds. What about 237? Yes? Wow. What about the rest of you? Have you seen it? No, you haven't. Okay. The proof is a bit annoying. But I should do it. I mean, it would be, you're a fourth year math student, and this is the one inequality you might actually use. Yeah, but then how do you know it's less? So perfect, yes. So the statement is A dotted B is less than the norm times the norm of B. Oh, okay, here's a quick way. Thank you, yes. Here's a way that you can save us time, because I've done this. This is equal to cosine theta, right? Remember? But this is less than 1. There you go. Cautious words. I mean, of course, all the meat is here. The way you get cosine theta is like, you've seen it, so I think. Okay, good. So this is cautious watch question. Then if you do cautious watch, actually, yeah, it's good. This is a good way. So you can use it in quizzes or tests. Namely, suppose you have a Hessian, and I don't know if we might give you some abstract Hessians. We'll see how far we go. This is a quick way to get no negative. Yeah. Okay. So, oh yeah, I should explain how this works. So, unless someone can figure this out. So this is the process works. How can we apply it to this to show that it's non-negative? What should be the AIBI? It's a bit tricky. I want to see if you can figure this out. Any ideas? What should AIBI be in terms of VI 0? What's the stupid choice? What? Is it hard? Is it hard? Okay, let me do it. So you see the upper bounds. So here's the choice. Take AI to be VI and take times square root of ZI and take BI to be square root of ZI. Okay. So let me prove you that this works. Summation of VI ZI can be split. Oh, and by the way, why am I allowed to take square root? Just to see if you are completely wrong. Yeah, yeah, okay, perfect. Thank you. This was this EXI over two. So we have VI square root ZI, and this is square root ZI. Apply Cauchy-Schwarz. You get summation of AI squared, square rooted. This is true for any numbers, right? So you can always use this. No requirement for it. Doesn't have to be exponential or square root or anything. And then plug in your numbers. So you get VI squared ZI and ZI. Okay. Okay. At least you have to see it once. So if it happens, if you get hit by lightning in your research, come back to it. All right. So this is supposed to be let. If you remember just a minute ago, I gave you a function whose minimizers were an entire set. This is a very common phenomenon, and there's a whole theory behind it. So take a convex set, take a convex function, that was a convex function, which needs to have a minimum, so it cannot just blow up to minus infinity. Then take all the minimizers. So this is where the function is smallest, okay? And yeah, so suppose this set is non-empty, then this set is also convex. Oh, and then you go, yeah, this is but even the gamma is convex, that's very beautiful. So if you remember in this, go back to this picture. Not this picture, this picture. The minimizer, I should just copy it. Can I copy it? No, because this is not. I know what to do. I'll copy it. So you have it in one place. Yeah, so gamma here will be all the x, y, all the 0y, okay, with y strictly positive. So you bring this line down there. All right. Yeah. And it's convex because it's the line. Any 2 points can be connected by a line. Good. So you have an example in your head. Now let's. Yeah, you can check, but this is stupid. I like the other one. Another example where all the minimizers are the entire negative axis. Where's my picture? I had a nice picture. The picture is like this. It goes like this, and then it blows up. And so gamma would be the entire negative axis. Is that okay? What question? Yeah, puzzle. You have a question? Oh, it's not? Oh, you have old slides. I updated. Yeah. Yeah. It's all I have updated on purpose. Because I wanted to give you an example. All right, let's prove that this guy is convex. Take a value from the set M0. So this is the minimizer for your guy. Okay. Yeah? It's globally convex, so there's only one minimum. Anyways, I think we talked about it. That's why I can take one value. All right. So yeah, you do this, and finish from here. Okay, can you remind me which result applies here? We proved something about, remember last time, sublevel sets, epigraphs. Yeah, so remember from last time, we proved that the sublevel set, which was subset, so anyways, we proved that this is convex. It was proved last time. Now let's do the next part, global min. Assume that it's not a global min, but it's local. Then what do you have? It means that suppose this is your function, which is not possible really, but I'm going to draw it now. So this is f of x naught, and suppose there's another place that falls below f of x naught. Like this. Okay, this is the f of y. Do you understand? So if it was a global min, there would be no such other point. Zoom. And then now let's see how convexity comes in. Just connect the 2 points. So let me draw that picture. This is x naught, and this is the f of y. Connect them with a line like this. And let's do the algebra. So this here, first step is by convexity, right? And the next step, you use that f of y is strictly less than f of x naught. Okay? So first step convexity, next to this, but then the s, 1 minus s cancel out. So you get this. Okay, yeah, can you tell me? I hope I don't say the next. Okay, yeah, someone who doesn't have the slide, can they tell me how to finish from here? What's the contradiction? So x naught is a local minimum. And we just proved that for every point in this line, f of x naught is above. What's the contradiction? What? How close? What was the definition of local min? I know I've asked it a couple of times. Huh? Yeah. So yeah, what's the definition? For x and what? Of what? Yeah, so you can, there is some epsilon naught very specific to x naught. So this epsilon is a function of x naught. And it's an unknown. We'll talk about later on about like minimal eigenvalue and stuff like that. But so you just need you draw your ball, and you need it to be you just take a point in here. So you take some value and you go down. So yeah, so you make it close enough so that it's close to the epsilon naught. Okay. Yes. So good. I didn't do too much. So in half an hour we'll have our quiz. You can stick around or go home. So we can use continuity to find a point near x naught where x naught should be a local min, but also on the line. Wait, why are you using continuity, Daniel? Is Daniel there? Oh. Oh, yeah, continuity of the line. That's right. Yes, exactly. Yes. Yeah. Which question? Why do you need convex? No, but why do you need convex? I don't know what the question was. No, I remember I thought it's not clear. Like, first one, what is yeah, the first question? What is the first question? What is it? What is it? Oh, I see. Yeah. And what about the second? It's from the physical direction. Yes, like don't go back. Oh, no, sorry, here. Like if you exclude plus something, the whole is available. Why people respond to minus two? And then this is like one. Yeah, and then you have like physical direction over there below it. All in the yeah, that's like the main beginning of the set, physical. Oh, here. No, but it was a result that we proved that it's making it. No other than the physical direction, needs to be autonomous, and there's a local name. Like, but that's how you get the second. You have two things. Yeah. So what is the number? Can you open this up? Yeah, can you? What would one of